Hi everyone, welcome back to Physics 2B. Today we are going to look at geometric optics. Now I wanted to make note that I will be going in a slightly different direction than the textbook this time, just because they go into a lot of detail that I don't think is really necessary for our course. So just make note of that when looking at the PowerPoint as well as the homework for the week, okay? So let's get started with the idea of light. So light will form images when they travel through lenses. So this is anything from your eye, a camera, mirrors, anything like that will form an image when when light travels through them, okay? And when we're going through this, we will talk about light rays or just rays in general. And that's going to refer to the straight line which the light originates from. Okay, so if we have, say, a bulb, a light bulb, that is going to be the start of the ray from the bulb to wherever that light's traveling to. Okay. And geometric optics is the part of optics dealing with the ray aspect of light. So we're going to be following these rays, see what they do when they interact with different mediums or materials. You'll hear me say mediums, and just note that that means the type of material that the ray travels through. Okay. And there are two laws that govern how these light rays um, change direction when it interacts with different mediums or matter. Okay, and these are the law of reflection and the law of refraction. Okay, so we'll get into those in a minute here. And I wanted to just point out this image here that we can have, or we have white light coming to this glass prism, okay? And as you can see, it changes direction slightly when it hits that glass medium. And because it is a prism, it will break up that white light into its component colors, and we'll see this nice spectrum of light, okay? So we'll look at this down the road a little bit. I just wanted to kind of give you guys a base idea of what we are looking at here. Okay. So let's first look at the law of reflection. Now, the main concept here is that the incoming ray of light will hit a smooth surface and reflect at that same angle, okay, or any surface really. So this one ray of light, the incident ray, we will say, okay, this is the incoming light ray, okay, it's incoming at some angle to the perpendicular. So this dashed line here is perpendicular to the surface. So we can say it's perpendicular to this surface, okay? So this angle here, theta I, should equal the reflected ray angle. So we have the incident angle, or incident ray, sorry, coming in, hits the surface and is reflected back at the same exact angle of the reflected ray. So this is the reflected, whoops, if I could spell, the reflected ray. Oh, that doesn't help. Or the outgoing. I just realized I put the same thing. I'm going to say the outgoing ray. Okay. This is the outgoing light ray that was reflected from that surface. Okay. So these angles will be the same due to this law of reflection. Now, suppose we have a rough surface. Now, a rough surface can mean anything from something that has very mild roughness, or something like this. This is a bit extreme looking. Like what I think this looks like is dirt, but it could even be a piece of white paper, right? Because um, how paper is made, it's just like a bunch of shred up, I guess, pieces of small pieces of wood, right? And so it's not going to be completely smooth and nice. So it's going to have a little bit of rough edges to it. So we will have these light rays coming in, say from a flashlight, and it will get diffused when it reflects from the surface, from the rough surface, because we have different angles of incidence, right? We have different incident angles. So, whoops, say for this ray here, we have this angle, right? So these two are the same, which is fine. And it hit the surface here, which if we put this here, that is perpendicular. Good. Now we have another light ray coming in, but now the surface is here, and so we have this perpendicular. So it's going to look a little different the way it reflects off. And so having all of these doing this, having all of these light rays that are coming in at the same angle, just hitting the surface differently, we will have a diffused light, okay? So if we look here at this image where we have this, I'm going to say this is white paper, like printer paper, right? And we do this experiment, we will see that it will be reflected at different angles here because of that. And so it won't be as, it'll be, the light will be diffused, meaning it'll be less bright, and it'll kind of spread out on the paper seemingly, right? But if we have something like glass, where we have a very smooth surface, so this is rough, this is smooth, okay, we will have it reflecting at one angle only. And so that's where we'll see the light. But if we go to a different angle, we won't see that reflection of light. Okay, so this is the idea of the law of reflection. Now let's look at the idea of refraction. So this isn't quite the law of refraction, but this is going to be the idea of refraction. So the changing of light rays direction, or the bending of light rays, when it passes through variations in matter, or variation of material. Okay, this is refraction. So if you want to look at an example here, we have somebody looking at a fish tank, right, with a fish, and this is where the actual fish is, okay, and he is trying to look at, see where the fish actually is, but he's seeing it from two, or he's seeing the fish at two different spots. Okay, so this light will change directions when it passes from the water to the air, or from the air to the water, right? So it is going to be changing direction, so he's not able to really see. A really good example of this would be either a straw in water, or a pencil in water. Maybe you have seen that, where, let's see, we have a glass of water. We'll stick, I want to say a pencil, but it really doesn't matter. We can use a straw too. If we stick it in there, it might shift slightly. Whoops. Um, and maybe it'll go more like that. Okay, this is a terrible drawing, but the idea is there that it changes the angle. So we have this angle going here, or the direction, I'm sorry. and then it changes there. Okay, so maybe if you've been like in a lake or any kind of body of water, maybe a pool, um, you can kind of see like maybe your legs look like they're in a different position than they should be attached to your body. This is the idea of law of refraction. So we're seeing it how it changes due to us looking at the light through the water. Okay, so with that, we need to know a couple of other things that are attached to refraction, which is first the speed of light. And the speed of light, c, is going to vary depending on the type of material that it's traveling in. Okay, and this is exactly the reason for why we have this refraction that happens, this bending of light. Okay, it's due to the different type of material, and that light will travel at a different speed. Okay, so this kind of sounds weird because we have just looked at the speed of light as being c, right? 3 times 10 to the 8th meters per second. But this is in a vacuum. So this is in a vacuum, or any kind of like empty space, right? So this is where we don't have any medium that light has to travel through. There's nothing there, so it just travels, okay, at this speed. Now, because of those or I guess I should back up. So the speed of light, like I said, will depend on the type of material, and that is because of the interactions with different atoms, crystal lattices, and so forth. So what does it mean by crystal lattices? That is going to be the shape of the um, um, not material, the shape of the, wow, I cannot, I'm looking for a word and it's not coming to me. Crystal structure, so molecular structure, there we go, molecular structure. So how these atoms come together and form some sort of molecule, right? These elements will form some sort of molecule, and how those fit together, these long lattices, will change that speed of the light. So we need to define a index of refraction in of a material, and we say that that is the ratio between the speed of light in a vacuum, c, divided by the speed of light in that material. So I'm going to say v, I don't know why I drew it like that, v is the speed of light in material. Okay, so that index of refraction is um, dependent on the speed of light in that material as well as the speed of light in a vacuum. It's a ratio. Okay, so what are these index of refractions? Maybe if we get some sort of number to them, we can get a little bit of a better feel for them. So let's look at table 25.1, which you will be using. Um, this is a big list of index of refractions of different materials. So we have the different mediums that it'll travel through and the indices. So for air, which is just our air, is going to be 1.000293. Okay, so it's pretty close then to the speed of light, right? Because this N is C over V. So that means this ratio is really close to 1, right? It's very close to 1. And if it's very close to 1, that means it must be that it's very close to our speed of light in a vacuum, okay? So why don't we make note of that? So if if n is closer to 1, the v is closer to c. So the closer the n index of refraction is to 1, then v, the velocity of the material, the velocity of the light in the material is closer to the speed of light in a vacuum, okay? So then we have a few other gases here. We have liquids. Here, let's look at water, fresh water. So that's not going to be like our ocean water, right? That's going to be our surface water. So maybe in lakes, rivers, wherever fresh water would be. It's about 1.33. Then we have solids as well, including ice, which is 1.309. So notice something very interesting, that looking at this number here, 1.309, and this number here, 1.333, light travels faster in ice than in water, okay? So just something a little bit interesting. And then we have other types of materials, different solids. Okay, we have glass, quartz, zircon, diamond, and so forth. All right, so let's look at an example. Let's calculate the speed of light in zircon, which is a material to imitate diamond. So let's see. So we know N is equal to C over V, and we're looking for the speed. So we would say this is V is equal to C over N, right? If I multiply V to both sides and divide N by both sides, this is what I'll get. And I need to find N for zircon. That is going to be 1.923. 1.923. All right, so V is equal to 3.0 times 10 to the 8th meters per second. And we divide that by N, 1.923. So let's do that. 3 times 10 to the 8th. Whoops. 1.923. Now I'm going to put it in scientific notation just so that it's easier to write. So I get 1.56 times 10 to the 8 meters per second. So notice a couple of things. First, this is less than the speed of light in a vacuum, which is good. It should be, right? We can't exceed the speed of light in a vacuum, okay? So maybe we should make note of that. So C, you can think of, is the speed limit, we could say, of light, right? That is the maximum speed of light. Okay, so it can never be more than C. So if you ever do a calculation and it's more than this value, 3 times 10 to the 8th, then there's an issue in our calculation, okay? So that's good. Another thing we should note is that the index of refraction does not have any units. Okay, so if we go back, we don't have any units for these indices. So I'm going to go ahead and say no units right here. Okay, so this is good. This means this checks out. We found the speed of light in zircon, and that is all. Okay, so I'm going to go ahead and pause here. Then we'll pick up next time with some more refraction and the law of refraction.